All right, couple things. As we get going here, you may have saw that this went up last night. I finally got my ducks in a row and got homework 6 and 7 up. So here's kind of how I just want to spend a couple minutes talking about how the next 2 weeks are going to go. So what we're going to have is we're going to have homework 6 and 7 is up, which is like the last two homeworks. And homework 8 going up on Thursday, which is going to be the stuff that we're working on this week. And both of those, so essentially 6, 7, and 8 are all due a week from Friday. The I think homework 6 is a pretty big one, but the rest of them are 7 and even 8 aren't really all that bad. They're pretty quick. But I think it's 6 is kind of a big one, like a long one. But you have quite a bit of time to get those done. But what I would want to do is recommend that you get those done as soon as possible for a few reasons. Because basically, coming up is we have the midterm next week, and so all this content is going to be on the midterm, and the midterm is going to go live on next Wednesday. So a week from tomorrow, it will go live, and then you have essentially till Friday night at midnight to get it done. We'll talk more about all the details about the midterm coming up. We're gonna spend on next Tuesday is all a review day. So we have class content for today and then on Thursday, and then next Tuesday is just a review day, and then there's no class the following Thursday because that's just you have that dedicated time to do the midterm. So but basically you'll have to get it done by midnight Friday or midnight on Friday night. That's the deadline. I don't want you to be working on this on midnight on Friday night. So I want you to get this done. In fact, the best time to do it would probably be during class time on Thursday because I know you have that time carved out for that. So it's going to be, you have to do it in one sitting. It's a 90-minute, basically you have to, it's written to be done in under an hour, but I'll give you 90 minutes to do it. So you have to do it all in one sitting, and it's all online. It's all through Canvas. Yeah. So, and it's going to be up through homework 8, which is what chapter is through whatever comb filtering is. I don't know what chapter that is. That's whatever we do not. I can't remember what the chapters are, but whatever the chapter is for this coming whatever we're doing on Thursday, that's what it's going to be up through. So we'll talk more about the logistics of it, like how many questions and all that kind of stuff, and how it's going to go down. We're going to talk about that later. But just so you know, kind of what's going on in terms of getting things set up. So, and then just as kind of a heads up for the week after that is, we're going to be running that class that week asynchronously. So I'm going to actually pre-record those lectures because I'm going to be out of town for that weekend. I will be available. I'll be online, but I will be out of town. So I won't be able to do my lectures live. So I'll pre-record those. And so, and they'll go live just like during normal class time. So it would be good to sit down and just watch them out. It's going to be essentially like what we're doing right now, but you're just not going to have all your classmates with you during that time. So, and that will be on Reverberation. So that's the week after the midterm. So, cool. Any questions on this, on the homeworks and stuff? Well, like on the logistics of what we're talking about, what we've got going on here. All right. It seems like a lot, but it won't be. The homeworks aren't too bad, so you can crank through those, and then that'll gear you up and get you ready for the midterm. So, cool. All right. Well, let's get moving on here. So, what we're gonna do today, this week we have kind of a lot going on here. So, what we're gonna be doing is I've got a couple things I didn't get to last class. I want to hit up on finishing up diffraction because I think diffraction is really interesting. It shows up a lot of places, at least in my world where I'm doing like loudspeaker design and measurement testing and that sort of stuff. Diffraction shows up a lot. And then we're actually going to get to refraction, which is chapter 8, and then diffusion, which is chapter 9. So, so diffusion, that's going to be a huge one. Diffusion is one of the biggest parts. Well, we'll talk about it. We'll get to it when we get to it here in class. But refraction, refraction's a pretty cool little thing, but not something that we deal with all that often, although there's some cool trivia with it. But diffusion is a biggie. And so there's a lot that I want to kind of drill down with this diffusion. So let's get into it. So diffraction continued because I didn't get through all the stuff I wanted to talk to last time about it. So remember when we talked about this, and this is a review from last time, but diffraction by apertures. So what I was talking about last time is that when we have an opening, that if you have an opening, if the frequency is much lower, meaning the wavelength is much longer than the opening, it's going to emanate as a hemisphere as it comes off this. So in fact, you see it right here. This is like, we can imagine my plane waves coming along from back here. And I have a tiny hole here, and then once it comes through this hole, it's going to emit as a sphere. And even though we call these plane waves, that could be also just a sound source that's really far away. And so that essentially that it's still like going to be a sphere, but because these spheres are so large, they appear as a plane wave. And then it comes through this little tiny hole right here, and it's going to emit as a hemisphere. And it's going to come through this thing. And so that's diffraction by apertures. So when we say that as the wavelength is increased relative to aperture, it tends to bend. So once again, the thing to remember here is that high frequencies beam and low frequencies bend. When I mean beam, it means they go in a straight line. So in this case, the frequency is small relative to the opening right there. So therefore, it's going to go straight through and it go as like a laser. Well, I mean, it's not like a laser, but like along that same kind of concept that it goes in a straight line. And you can get the, like, if you were like, if you know this effect. So if you have a hole opening in a hole, like, so say we have a hole right here and I have a speaker or like some sound, maybe a band is playing on the other side of this or whatever, a generator's on the other side of this thing. Is if I walk off to the side of this thing, you hear it gets dull and muffled. And as I get closer to being straight on, it gets brighter sounding. And that dull and muffled, meaning the high frequencies are rolling off. And then but the low frequencies are coming out as a hemisphere off this thing. So they're going in all different directions. They're bending as they come through here. So you can hear the low frequencies all over the place, but the high frequencies, you have to be pretty much straight in front of the thing. And so this is the same reason that, sorry, I didn't see the chat there. So there could be a formal study guide. There's not necessarily a formal study guide. I'm writing two study guides right now though, concurrently. I'm writing one study guide for decibels, and I'm writing a study guide for the Fletcher-Munson curve, just because I feel like those need some extra like boost. But there's no study guide for the entire exam. It's just going to be on those two specific subjects right there. The study guides are going to be basically your homeworks. And so that's basically what you're going to be using as the study guides. So but in terms of like an actual study guide, I am writing a study guide on like a how-to on decibels, because I know that's still like causing some strife for a lot of people. They're like, there's just so many different ways you can ask the same thing. And the same thing happens with Fletcher-Munson curves. I know like the equal loudness contours, that causes some stress. So I'm writing up for like a little guide for those sort of two things. They're going to be kind of like just guide to decibels and just guides to Fletcher-Munson curves. So it's going to be something that it's not necessarily specifically for the exam. It's just going to be a general one, but obviously it's going to feed towards the exam type stuff. All right, so back to this diffraction thing. Basically, yeah, as I get in front of the thing, it's going to get brighter sounding. As I get off the side, it's going to get more dull sounding. And once again, this is why like low frequencies are very pervasive. This is why we can hear the low, like if somebody's got a bump in car system, that you can hear it pretty much anywhere, because those large waves, those large wavelengths, they wrap around everything as an object, and then when they go through an opening, they wrap around. And like I remember when I was a when I was a teenager, when I was younger, I lived in the basement of my parents' house, and I had a pretty decent stereo there, and my parents would be upstairs and they'd be like, "It is so loud, you're like ruining your hearing." And I would go downstairs. I'm like, "No, it's about the same loudness downstairs as it is upstairs." And that's because those low frequencies would travel up the stairwell and go out into the kitchen. And my parents are like, and to them, they're thinking in their intuition is be like, it should be much quieter. But those low frequencies, because they're so pervasive, they wrap all over the place. And the same thing goes like why, like, if you have a stereo playing in one room and then like you have like in another room, you can just hear that those low frequencies travel all over the place. It's just low frequencies are really, because those wavelengths are so long, they're like tentacles. They just wrap all over the place. They go everywhere. So I've got a lot of latency right now. Yeah, something is very strange going on with my computer. Let me try this. Hopefully we can power through this. So let's think about this like loudspeakers as virtual apertures. When you remember, like, I don't know if you remember back in the old days when we watched like Looney Tunes, but like one of my favorite things, like especially when you watch like Roadrunner or even like Bugs Bunny and that kind of stuff, they would always have that like hole where you could basically have a hole that you could just slap up on a wall. Like it was always like I think it was like Bugs Bunny's kind of getaway, or I think they also did it in Roadrunner a bunch too, where basically they would have like a hole that you could basically open it up and it's like a portal. Remember that game Portal where you could like basically jump through other areas? Well, it's like this hole that you could slap on a wall or on the ground and you could jump into it. Well, if we think about that, speakers are kind of like this virtual aperture. So when we play it, we've got a speaker right here. It's playing along here, and you can think about it essentially like being a hole to another universe. And if I'm playing music, like, you know that there's not a band playing on the other side of this, like in this tiny box. But I mean, go back a couple hundred years, or go back 150 years, and if you were to play like a speaker, people, it blow people's minds that there's sound coming, like a voice coming out of this, but there's no voice, or that there's music coming out of this with no music. But we can kind of think of like mobile apertures. So like, so wavelengths that are larger than the diaphragm, like, come out as a sphere. So in other words, if this were like a hole and I play a low frequency, it's going to wrap around and it's going to emanate as a sphere. Whereas if I have high frequencies that come off this diaphragm right here, they're going to go in a straight line. And you can try this out. Like, next time you have around a studio monitor, start playing some music and just walk around the side, go off to this off the side of this thing, and you'll hear it get dull. And then as you get in front of it, it gets brighter again, and then dull. If you go around the back of it, it'll sound like low frequencies. Like, you'll still have reflections off the walls that like will be high frequencies, but this is exactly why you can't, the low frequencies emit as a sphere, and high frequencies go as a beam. So low frequencies bend, high frequencies beam. So kind of cool, just a little thing. And then we also have this thing right, like the human head right here. So it's like we have this diffraction around the human head. So this is the basically kind of goes back to localization here. So we have like, we can see that the like around 1 kilohertz right here. So what is this? Which one is this? The black one is, let's see. So I could say low frequencies below 2 kilohertz diffract around the head, and high frequencies cast an acoustic shadow. So once again, that's because it's 17 millimeters and that's 2 kilohertz. So, and it's a gradient. It's not black, like black or white, where it's like, it's acoustic shadow or not acoustic shadow. It's kind of this little gradient around that region. But what we can say is that the 2 kilohertz is like the threshold. So anything above 2 kilohertz that's where we use like interaural level difference. Anything below 2 kilohertz that's where we use interaural time difference. But in truth, it's kind of this smeared area between the two of those right there. So pretty cool stuff though. So diffraction by low frequency, this is the same thing by cabinets right here. So low frequencies travel across the face of the speaker. And so this is, I guess I should have had this other speaker business here. But what we say here is that low frequencies travel across the face of a speaker and emit as reflection at the edges due to impedance difference. So it's kind of weird to think about this, but when low frequencies emit as a sphere, so if I go back to this picture, low frequencies are going to travel across here. And what happens is when they actually hit this corner right here, they actually re-emit. And so it re-emits again and acts as a secondary sound source. So because of the impedance difference. And the result is that we get areas of constructive and destructive interference. This is what we're going to talk about all next class. This is comb filtering right here. So we're going to spend a lot of time talking about this next class. But I just thought it's a little bit of an interesting bit of trivia. In my world of loudspeaker design, I spend a lot of time thinking about this stuff. So basically it creates a comb filtering effect. So smooth rolled edges mitigate this effect. So one of the things that you should be looking for in your monitors is rounded edges. And if you think about something like, well, you just look at a lot of them like Adams, or like a lot of, well, even like the newer Genelecs or KRKs, or, think about any kind of studio monitors that you have, they're almost always going to have this bevel, like a rounded bevel on their baffles. And the reason it does that is because it makes it so that it reduces this business right here. So that's a little bit of trivia. Not really that important, but I think it's just kind of cool. So diffraction by various objects. So like if we look at like sound level meters or measurement mics. So this is a measurement mic. Do I have one in here? I have my measurement mics around here. I think, is it in here? No, I don't have my measurement mics in here right now. I'll be talking about those next class. But measurement mics. So we've seen these right here. So this is an Earthworks M30. I have one of these. I love this microphone right here. If you look at measurement mics, they have this really tiny small head up at the top here. And the reason for that is because it mitigates the diffraction. So what I need to do is I need to make the head of this thing smaller than the highest frequency that I want, or smaller than the wavelength of the highest frequency that I want to capture. So if I want an omnidirectional mic like this one right here, I have to make the diaphragm super, super, super tiny and rounded so that it mitigates some of these diffraction effects. So we'll come back to more to this. We'll talk more about measurements. We're going to spend a lot more in the latter half of the semester talking about room measurement, and we're going to start in on it today, but we're going to talk more about it later. So I just wanted to kind of prime you with that. But diffraction, it shows up in a lot of different reasons. A lot of different places for reasons that are, once you kind of understand diffraction, you start to see it like all over the place, like how do we mitigate it and how we deal with it. So cool. All right, let's move on. Let's talk about refraction. So refraction. So we've got like diffraction, refraction. So refraction of the waves. So this is important right here. The definition is the bending of the waves due to change in medium. So what we could say is diffraction is the bending of the waves or beaming of the waves due to aperture size and object size. So it's basically wrapping around waves, wrapping around objects or wrapping around out through holes. So that's diffraction. Refraction is going to be the bending of waves due to the change in the medium. So like, what does that mean? So wave changing direction as a function of the change in the medium. So change in the density results in the change in velocity. So up to this point, we've said that like when we're talking about sound waves, we're talking about sound waves as being 344 meters per second. That's just kind of what we're saying. But that's not always the case. So now we're going to look at some cases where the medium changes, and there, as a result, the speed of sound changes. And as a result, it's going to bend the wave. So not to be confused with diffraction, change direction due to obstruction, edges, and openings. So refraction is changing because of the medium. So if we look at right here, this is an example, like a visual example. Like if you put a straw in a glass of water and you look at it, the speed of light is much lower in water than it is in air. And therefore, what it does is it's going to bend the way that when it goes through the light. And we can look at prisms do the same thing. Like prisms actually bend it and then spread it out by going through a couple different angles. But what we're doing here is if you're like, and try this out for yourself, like take a glass of water, throw a straw in there, and then look at it from different angles, and you'll see it looks like it's bent. Or the same thing happens if you look at somebody standing like in the shallow end of a pool, and you look at them, it looks like they're bent funny, or it looks like they're shorter or squattier. And that's because, again, it's bending the light. It's changing the speed of light, and therefore it's bending the direction, and then it gives us this weird visual look to it. So, well, we said refraction is solid. So proportional speed is higher in more dense material from high to low waves. Let's do this here. So I said solids, but it doesn't have to be necessarily solids. It could just be more dense. So solid is just a more dense form. We have gas and liquids and solids, but those are just essentially different densities of materials. So if we want to think about like gases or liquids, or even just different densities of different gases, those all they all kind of work the same way. So from high to low density waves bend down and towards, from low to high density waves bend out and away. So in other words, this is a dense medium right here, and this is a less dense. It's going to bend that direction. So if it were dense, if this were lighter and this were denser, it's going to bend this direction. This is denser and this is less dense, it's going to bend that direction. So let's take a look at this. I'm gonna hop out of this. Let's hop out. I'm gonna switch over. Whoops. Let's look at ripple tank for a second. Take a look at what's going on here. So my computer's acting really funky today. Let's see if I can find it. Let's do this temperature gradient. No, let's try and do one source, one frequency. Sorry, I can't find the old. Let's see, force of double slit. Basically, I'm trying to find slow, medium. There we go. Okay. So here's what we got. We have two different mediums right here. So we have our sound source cruising along right here. Make this a little bit bigger. And what it's going to do is it's going to hit this source right here, and it's going to move slower. And therefore, what it does is it looks like it compresses the wavelength. But what's interesting about this is that this is putting out a frequency, a certain frequency, and you can see that the wavelength is shrink, but the frequency is still the same. So if I were to put my mouse here, it goes boom, 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 boom. It's when it hits the black and goes boom, 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 boom. So the frequency remains the same, but now it's compressed right here. So let me do this. I'm going to change this up into let's see if I can change this to a plane wave. So what did I say? Do a temperature gradient 2 demo. No, I'm going to do this one. So slow medium preset with the partial reflection. Okay. Oh, there's a refraction preset. Should be able to find it in here. I wish it were in alphabetical order. Oh, there it is. Okay. So here we go. So what I'm doing is I'm doing essentially like the equivalent of making a plane wave right here. And it's cruising along, and we can see as it hits this more dense, it's going to change directions. So it's cruising along here. It's doing this kind of pulse. And we're not doing it as a constant. We're just doing pulses so we can see it a little bit easier. But we can see that it basically changes direction and it moves down. So this is the lighter, this is the more dense, and it's going to turn itself down into the medium. And again, it's just kind of it just bends itself down in there. And so like if we do something here, where was that one? It was I want to find one with the anti-reflective. When I was doing dang it, which one was that? Sorry, I should have written this down. Slow medium. Really annoying that they don't have it in. I guess it's right here. So when I did this, you'll see that it actually bounces back. It reflects. And this goes back to the idea of when we were talking about like when I yell in water. If I yell above the water and I'm yelling to somebody underwater, some of that sound is going to go down, but a lot of it gets reflected. And that's because we have an impedance difference between the two of these. So because this vibrating air kind of sees this almost as a hard surface. And so some of it's going to propagate into it and get transferred into the medium. Some of it's going to get reflected there. So if we do where's the one with anti-reflective coating? Let's see if I can find that one. Basically, they have it. Let's get English mirror. Oh, there it is. Okay, cool. So right now what they did is they have an anti-reflective coating right here. So it's going to do the same thing, but now it's going to transfer more of that energy down into the system here. You can't really do this with acoustic systems so much. Well, you kind of can. This is what actually if you want to think about it, the flare of a horn is actually kind of like an anti-reflective. I know it's kind of weird to think about it, but the flare of a horn is an impedance matching tool, so it allows the internal waves to escape the horn. Otherwise, if you don't have that, if you just like say play on a trombone slide and don't actually have the bell attached to it, it's really quiet. So by flaring the horn is an impedance matching tool and it allows it to propagate through the system. The same thing happens like even on eyeglasses. So you want like glasses to be like transmit as much light through your specs as you can. So what they do, you don't want it to reflect. And so what you do is they put anti-reflective coatings on there, and that's going to make it so that basically that light gets through and not reflect off of your glasses right there. Same thing on camera lenses. On camera lenses, if you look at camera lenses, they kind of have like a bluish green hue if you look at them from the side. That's an anti-reflective coating. It's basically what that is. It's an impedance matching tool. So it allows the energy to pass into the medium. It's going from air to glass. We want to be able to we want that light wave to be able to pass through that very, very easily right there. So, but for us in terms of acoustics, what we care about is basically this slow medium. Let's do refraction right here. What we want to say is that basically it bends in. So let's take a look at this as an example. Let's stopped. There it was. I don't know why I couldn't find that before that stopped. So let's take a look at this. Where does this happen in terms of acoustics and in real life? Well, if we do refraction in atmosphere, where we see this, temperature changes cause a change in wave speed. So what we said is that the wave speed is 344 meters per second in air. But we've also said that that changes as a function of temperature. So if it gets cold, it slows down. In other words, it becomes more dense. And if it speeds up, or if it warms up, it speeds up and becomes less dense. So therefore, the speed of sound decreases in cold air and increases in warm air. So the result is so if I have a sound here, so this is from the book, and basically if I have a source and a receiver right here, we call this wave fronts, but we can imagine that it's actually, a sphere emanating off the source right here. And these are the wave fronts that we can call those the compressions for whatever we want to call them. And they travel essentially in a straight line. I mean, it's a sphere, but if we imagine one particle like beam, it's going to come off as a straight line. But now if we have cool air below and we have warm air above, what it's going to do is it's going to bend the wave as a result. And so therefore it pulls the energy down. And if I have cold air high up and warm air down below, it's going to spin up. So think about this. Where does this actually happen? Well, if you're like at a lake on a warm summer day, so say you're at a mountain lake even. So a mountain lake, mountain lakes tend to be very cold. If you've ever gone swimming in a mountain lake, you can attest to this. It is cold. So what it does is that cold water cools the air above it. And as a result, what it does is it bends the energy down. And I think I have it right here. So this is what whoops. I lost my keynote. Where did that go? Keynote was acting funny there. So, where am I? So what we've got here is this cool air. So as I've got a sound source here, they come up here and it bends itself down here. And as a result, what ends up happening is more sound waves get bent down there. And so therefore you can hear it really well. So again, using this lake as an example right here, you can hear somebody talk across a lake. So if you've been camping, if you camp on a mountain lake, you can hear people talking across the lake almost as if they're right there. It's bizarre. You can hear people, because what it's doing is it's bending the energy of the waves back down, and it's creating a lot more energy. It's going to be essentially basically focusing a lot more of that energy is going to focus itself down around, and you're going to be able to hear people speaking across a very far distance, like really apparently. It's really crazy. Like it's quite weird. And then if we have an inversion there, so maybe you're on a concrete parking lot. So maybe you're like out there and it's like not concrete, but like a blacktop in the summer where you have maybe in the summer where it's out in the evening where it's like the sun has just gone down, but it's been a ripping hot day, that if you're not like the concrete is still just baking hot, but the air is a little bit cooler. You can be across a parking lot and people can be yelling and you can barely hear them. You can't even hear them because it essentially creates an acoustic shadow. Even though I'm standing right here and the person's yelling right here, their sound waves are bending up because of this change in density, that it bends up, and therefore I don't end up hearing them. So it's kind of this weird effect. But this, where you the example I gave you is going to be where the most effect, where I think you'll see it, is like here. Is like mountain lakes is where I've heard it like really apparently. It's pretty crazy. So let's take a look at this in terms of the ripple tank for a second. So if I do this one right here, temperature gradient right here. So what I've got here is I've got cold air down here, a warm air up here, and let's get this thing going. Let it do its thing. So again, this is the example where I have cold air, like this would be like the lake. And what I did is I put up a barrier right here. So if I have a source right here and I'm right over here, what's going to end up happening is, I wish I could speed this up a little bit. Let's speed this up a touch. And watch what happens here. It bends it down. And as a result, if I'm standing right here, even if I have a wall in front of me, I'm going to be able to hear that person plain as day over the wall right there. And this is the frequency independent. So it doesn't matter what the frequency is. Whereas like diffraction is frequency dependent, refraction is frequency independent. So I can I'll be able to hear them really, really well. So, okay, let's do this one. So this is if I have dense air here and warm air here. What it's going to do is it's going to bend down into this area here. I guess like if I'm standing right here, I'm not going to be able to hear it very well. It bends it away. So I might be able to get a little bit of it, but for the most part, this is that acoustic shadow that we were talking about right here. So even though if I'm standing right here, it's going to bend it away from me right there. So basically, I'm not going to be able to hear anything. It's silent right there. Oh, that's kind of interesting. So it's going to bend down and then back the other direction. Speed this up. So it's going to bend it and then it's going to change it back. So it's going to change back to the same original direction right there. Kind of interesting. Another temperature gradient. Yeah, this is another one. Same deal. It's gonna bend down and then it's gonna bend away. So the idea behind this though is, well, I guess not behind this, is that basically, that's all. That's basically what we're saying is that it's changing as a function of medium. But the truth is we don't run into this except for when we're outside. So how does this affect us as audio engineers? Well, it may affect stuff if you're doing a festival and you're doing it on blacktop. It could affect your sound a little bit there. So yeah, so like if you're at a festival and it's not a massive wall of speakers, it will actually if you're like a massive blacktop and it's getting baked all day, it is going to bend waves up and into the atmosphere, and that means it's going to be really annoying for people who are farther away. But for people who are like right there, it may bend up and you may not actually get a lot of you may be losing a lot of like sound energy to refraction, but that's not all that often that you find that. So look at wind effects. So not exactly refraction, but the thing is the same. Because we imagine essentially that when we were saying before that the waves are, the medium itself doesn't move, but the waves do move through the medium. But what if the medium itself is actually moving? So in the case of wind. So if I have a sound source here and I have a wind and I'm upwind from that, it is going to bend. And this is because of the way the wind is actually swooping up. It's going to be bending the waves away from you. So therefore it is going to be like hearing stuff upwind of something is going to be harder to hear than if you were downwind from it, where you're going to be getting more of that. Where basically if I'm downwind, the reason for that is because if the wind is going this direction, what it's doing is I have a lot of friction from the wind. The ground creates wind friction. And so therefore it's kind of, you can imagine the wind is constantly tumbling down towards the ground because it's got more friction. If you've got something that's pushing down on it, like if I've got a surface, it's going to be pushing down on it. The friction causes it to constantly roll down. And therefore it's going to create this bending of the sound down in this direction right here. So kind of interesting. Even if we were going straight up, that because of the medium itself is moving, it's going to be bending in this direction right here. So kind of interesting stuff there. But let's talk about enclosed spaces. So in enclosed spaces, it's not a very significant deal because, like, if we imagine HVAC systems are constantly circulating air. So we know that the hot air, if I was in a space like giant auditorium or gymnasium, that the hot air is going to rise and the cool air is going to be down near the floor. And the result is that we would get that same thing. The sound would tumble towards you, or it would tumble down, and therefore you would hear it better, generally speaking. But, like the thing is, if you're in a gymnasium, you have so much reflection and so much bouncing that you wouldn't even notice it. And usually gymnasiums aren't that big enough that you could actually notice this. Maybe a giant warehouse, you can notice this. But the HVAC systems that are constantly circulating air, they reduce that gradient above at the height and below. So you're really not going to really run into this very much as in enclosed spaces. So as an acoustician, as an indoor acoustician, as most of us are, you're not really going to run into this sort of thing very often. But it's something to know that if you're working on a really, really, really old building that's really big that doesn't have good HVAC, I suppose you might run into something like this, but I don't know. Not very often, I don't think. So, all right, my friends. So that in a nutshell is refraction. We could go on and we could do a lot more experiments with this, but I think you kind of get the gist. The main takeaways are it's just a changing as a change in density, and that basically I want you to understand that it tumbles down with cold air below and warm air up, and tumbles up with warm air below and cold air above. That basically, I just want you to understand that direction of which that's going. So cool. All right. Now we move on to what I think is one of the most important parts of our the semester. When we talk about diffusion. So diffusion is one of when we talk about the tools as an acoustician. So what we're doing, I guess, kind of the long game here is I want you to be able to tune rooms. So by tuning rooms, which is a weird thing because rooms don't make sound themselves, but they do resonate and they do affect the energy inside them. They affect the sound energy. So what I want to do here is I want you to be able to go into a room, whether it be a recording studio, a living room, a garage, a concert hall, or whatever, and be able to deconstruct and be able to go consult if you want to. So as a side gig, I do a lot of kind of consulting, acoustic consulting, and it pays really well. And it's incredible with just a little, with some knowledge and about $200 worth of gear, you can start charging $100 to $200 an hour for this stuff. So, and I want you to have that ability, and I want you to start, I want you to try it, make a run at it. So, because once people start learning that you know how to tune rooms, you can do quite a bunch of cool stuff. You can make some pretty good money at this stuff. And it's not, I won't say it's difficult, but it's not that difficult. It's all the stuff we're learning in this class. So boom, let's make some money. Let's make some money off this stuff that you learned in this class. Maybe you're sweet. So when you walk into a room and you go, okay, I need to treat this room, you essentially have a few different tools in your basket. And when we talk about critical listening spaces, we have diffusion and absorption. Those are our main two tools that we have for everything that we do in acoustics. Not for everything, but for a lot of what we do in acoustics. So diffusion is where we want to keep the energy in the room, but we want to spread it around. And then absorption is where we want to remove energy from the room. So basically we talk about sound as an energy, and we think about that do I want to keep the energy in the room, or do I want to get rid of the energy? And when we say I want to keep the energy in the room, usually when we say I want to keep the energy in the room, we have to add diffusion. So diffusion is meaning I want to spread the energy around the room evenly. And so if you think about something like a concert hall, so you want everyone in the concert hall to have the same experience. So that means you want everyone to have the same diffuse properties. So in other words, we want the energy to be all around the energy. We don't want one part of the room to be like super loud at 50 hertz, super resonant at 50 hertz, and another part of the room be super dead at 50 hertz, like in the middle of the room. So your job as an acoustician is to spread the energy around. And what the term for that is diffusion. So we want to diffuse the energy and pull it around here. I guess it's funny when you think about like diffuse, like to diffuse a bomb is DIF. It's only one F, I think, in that. It says defuse. Diffusion is different. It's where you just spread the energy around. So yeah, disperse it evenly. So the goal is to have even distribution of energy throughout the room. But it's important to understand that this stuff is frequency dependent. So when I spread the energy around, like we want all the frequencies to be spread around around the room. And we're going to start using that reflection knowledge that we learned last week and put that to work for us. And we're going to look more at like shorter diffusers and look at some more complex, and there's some fancy ways to do diffusion. We're going to look at that later, but we're going to start we're going to bring it out today to talk about, we're going to talk about the tools for diffusion a little bit later, but well, we'll talk about a few of them today. So this is a kind of a wordy list here, but this came out of the book and it's wordy, but I want to kind of go through it here for a second. So frequency of spatial irregularities obtained from the steady state measurements must be negligible. So what they're saying is that basically, so steady must be negligible. So a steady state is meaning basically where I'm blasting sound and I'm moving a microphone around the room. That spatial irregularities obtained from steady state. So basically that it should be pretty much like the reflections and the standing waves in the room shouldn't change. So in other words, if I take a microphone and I move it around the room using, like if I'm blasting pink noise. So what they mean by steady state measurement right there is steady state is they're blasting pink noise with a microphone. And you're just blasting pink noise and you walk around the room with with the microphone, your readings should stay the same. So in other words, if I get near a wall and it changes, and if I get near the middle of the room and it changes, that means it's not very diffuse. That means that there's buildup of energy at certain areas of the room. So we don't want that. So beats in the decay must be negligible. So in other words, if I blast pink noise and I stop, that the energy as it decays out of the room, we're going to talk a lot more about energy decaying in the room next week, or actually after the midterm. We talk about reverberation. That basically that energy will kind of beat. It decays off as a beat, kind of like echoes. And we don't want that. That's a bad thing. We want it to be a smooth decay. So when I turn off the sound, I want the energy to decay out of the room in a very smooth fashion. That's what they're saying there. Decays must be perfectly exponential, so it appears straight on a log scale. So in other words, like if I have two rooms coupled, if I have a room next to another room and they have two different reverb times on them, you're gonna see like a curve, like a bend in the energy decay. So that's bad. We want that to be like a smooth exponential decay. So again, we're gonna talk about this later. But basically, when I turn off a sound, the energy decays exponentially. So reverberation decay must be same in all positions in the room. So that's kind of tying in this stuff. So that basically there must be no beats, and also that the energy is all the same throughout the room. Character of the decal be essentially for all frequencies. What did I misspelled there? Oh, decay. Yeah. The character of the decay would be essentially the same for all frequencies. So character is kind of like, it means the rate of the way. So character of the decay will be independent of the directional characteristics of the measuring microphone. So using an omnidirectional microphone, or even if I use a directional microphone, it should be all the same, and no matter which direction I point this thing, like if I use a cardioid or something like that. And the character of the decay will be essentially the same for all frequencies. So what we're looking for there is the character means, like, I guess, the rate of decay. So we want them to, our goal is to have a constant energy decay. But that doesn't ever happen. We'll see why here in just a little bit. But those are what we're looking for. So that's our kind of our goal. So when you walk into a space, if you're talking about a concert hall, then you want to try and create this stuff, this is what you're looking for right here. All right. So evaluating diffusion in a room. So sweep a sine wave. So here's how we do this. So sweep a sine wave through a speaker into a mic that measures the amplitude per frequency, checking by position throughout the space for uniform energy and decay times. It's never perfect because the speakers aren't perfect, nor is the mic. So let's do this. So this is our first foray into understanding how to do this. So what I'm going to do, and I don't have it installed on this computer. I don't think we need this right now. Let's quit Ripple Tank because that's just eating up CPU. Let's go check this out. What I want you to do, and if you want to get into this stuff, is Room EQs Wizard. Ooh, my computer is chugging. So I'm going to post this link, but I want you to like take a look at this. This is this software right here is amazing. This is what I use for doing room acoustic software. It's completely free. Hell yeah. So let's download this thing and take a look at it. Let's download it. It works on Mac, Linux, and Windows. Runs on Java. Come on. Did it go? Okay. My computer is chugging today. All right. I don't have it installed on this machine. I don't do acoustic measurements on this machine because usually I do it on a laptop. Like my laptop has it. Come on. Sorry, I got a sidestep here. Let's see what's taking up so much CPU right here. I don't know what's eating up all my CPU. Come on. Yeah, something's just going on behind the scenes there. It's being weird. Okay, anyway, let's go to my downloads. What's going on here? So open when done. Maybe I'll get it going again. Something seems wrong here. Well, if it can't go, I don't know what's going on here. Come on. Try a different browser. Like everything is taking like 5 seconds to load here. This is weird. Crawling along here. All right. So while I'm doing this, what I think you should do is go to roomeqwizard.com and download this. I will post. I don't have anything to post right yet, but it's pretty fun to like experiment and play around with this thing. All right. Here we go. What is taking? Yeah, my computer's just bonkers today. Nothing is working. All right. Well, let's see if I can get this thing to work. Normally what I would do is just quick restart my computer, but since I'm on a Zoom call, I can't really do that. Something going on in the background? Oh, my FaceTime is running. Oh, come on. This is stupid. Why should totally be going? One more time. I'll see if I can find out what the culprit is here. It's not giving me much info. Windows Server, VT Coder, XPC. I don't know what any of these are, so I'm afraid to kill them. Okay. All right. Well, I'm gonna have to move on right now. So just because I can't get this thing going. But basically, what we do is we use this Room EQ wizard, which is, well, let me pull up the page again. So what Room EQ wizard is essentially it's a way to do this sine sweep. And maybe since my computer's not working today, I'll get it set up for next class and do a sweep with this thing. But basically, it's pretty cool to see how to go through this. But basically, they show in here with a little bit of equipment. So mini DSP, there's a calibrated USB mic you can use. But we also have the Dayton audio. This is like $45 or maybe $50 or something like that. And a couple interface. So an interface. So if you have an audio interface, you're off to the races. So there isn't really much more you need to do it. Oh, cool. They have, look at that, recommended reading, Master Handbook of Acoustics. And this is an amazing book as well. Basically what you're going to do is take this, and it does this fancy thing. It goes wheat, and basically it takes a sine sweep. And what that does is it basically puts that all back to time 0 and essentially creates an impulse in the room. And then basically what an impulse is it's all frequencies at the same time. So you can also do an impulse like a balloon pop. So the old school way of doing this kind of thing would be to do a balloon pop. And it's still used, and I still do that occasionally. We'll use a popping balloon. So a popping balloon essentially is a pulse, a burst of energy. And a burst of energy is all of the frequencies at the same time. And what you do is you burst the energy, and then you listen to what happens to the reflections afterwards. And so you're looking for things like the beat frequencies. You're looking for the rate of decay. Yeah, and man, I wish I could do the demo, but what we're looking for here is basically, this is a kind of a crummy way of looking at this, but basically what we're saying here is if I look at the frequencies, like we're looking at the rate of decay, and so they're showing this as broken up as frequencies here. So it's 63 hertz. What they're doing in this case, basically they're doing a steady state. You blast pink noise and then you turn it off, and you look at the frequencies as a result afterwards. And so you can see these little hops right here. So that means those are beat frequencies. That means 63 hertz is echoing in the room. It's going woo, woo. And so if I had a microphone right here, that 63 hertz is going to be getting louder and quieter and louder and quieter as it moves around the room. And as we go up in frequency 125, so it's getting smoother and smoother and smoother and smoother. So, and that's because at low frequencies, these long wavelengths, they tend to like have some of these echoey kind of probabilities. Oh, so this is 63 hertz right here. Yeah, so we can see this got some huge beats right here. Those are what we don't want to see. So what we want to see is a nice smooth uniform right there. But what we usually do is we look at this in terms of like, I'll see if I can get it to show here. But this is what we call a waterfall graph right here. And let me see if they have some images. I'll just Google it. Here we go. So what we see here is, let me open this in a new tab. Zoom in on this a little bit. So what we can see here is we have frequency down here, we have amplitude here, and then we have time in coming towards us. So it's a 3-dimensional one. And what we can see here is that what we're looking for is smooth here. So what they're saying is like, we can like, oh, see like this right here, this is that beat frequency that we're talking about. That's something weird, 200 hertz. That's strange. Something bizarre is happening right there. But these are like beats. But basically what we're seeing here is that we're looking at the rate of decay for different frequencies. And so what we want to see is we want to see smooth, like the goal is to find a smooth, uniform decay across all of these. And you can see that the frequency response, so this is the frequency response of the sound system, is crazy all over the place. So what we want to see is we want to see flat and smooth is what our goal is. But this is pretty typical. This is kind of real. So we see that right now at 70 hertz, we see 70 hertz is hanging on for a really long time. And then we can see something down here. This is kind of probably just weird energy down here. But what we're looking at here, like this 70 hertz right here, that means that they need to do some treatment for the 70 hertz in this room right here. Not in terms of diffusion, but in terms of probably absorption. But what we're looking at here is all three of these at the same time. So when I'm over in keynote right here, what this is doing is that we're plotting all of these instead of plotting these separate from one another. What we do is we turn them all and face them towards us, and we look at this energy as it travels towards us right here. So the waterfall image is usually where we're going to see most of the decay kind of stuff. That's what we're really going to be looking at here. So if we look at the total summed energy overall, so energy, so this is looking at what are those statements they said? So the energy in the room should fall at a constant exponential rate. So plotted on a log scale, that should be ideally as a straight line. So slope determines the reverb time. So what we have here, and this is what they're doing in this plot right here, they're doing a steady state. So I guess I should say, go back to what I'm saying here. There's two essential ways we can measure the acoustics of a room. One is doing a steady state measurement, where what we do is we do like pink noise. So what we do is we take pink noise, we blast it into the room, and then we turn it off. So what we do is we add energy into the room, and we just keep adding energy in the room with the speaker, like at a constant level, and we turn off the speaker and record what happens. So we can see that we have pink noise going right here, and we stop. And what happens is that the energy starts to fall, decay. This is not frequency dependent right now. We're looking at all the energy in the room. And so what happens, it falls off right here at a constant rate right here. And then we see that we have a second one right here. So this is not ideal. This means likely we have something like coupled spaces right here. So we're seeing the reverb of one room, and then we're seeing the reverb of another room right here. Ideally, we want to see a constant straight line go down right there. And that happens for the most part. But then it eventually will it goes down, and then it levels off because we actually have noise, in the room. Like the room has a room noise of about 50 hertz or 50 decibels or something like that, 50 dBSPL. So it's going to level off. But during that decay, it should be on so because we're on decibels. Remember, decibels are a logarithmic scale. So this should show up as a straight line right there. Yeah. So when low modes don't have absorption. So yeah, so this is we talk about room modes coming up. This is from another, there's a lot of things in acoustics that are kind of all tied together, and we've talked about this a little bit right here, but we haven't hit it quite. We're going to really drill down on this a lot more coming up in a few weeks. All right, so spatial uniformity. So what we want to do here is take lots of measurements throughout the space. So reverb decay should be on the same throughout the entire space. So high frequencies are usually pretty good. Low frequencies are challenging because of room modes. And this is for small room acoustics. Room modes are room resonances. So just getting ahead of ourselves, but we'll just kind of define it right now. A room mode is like when we talk about modes of oscillation of a string, like we talked about that at the beginning of last week. So a string has certain modes of oscillation that it will vibrate at. It resonates at. I can't make a string vibrate outside of its normal modes of oscillation. Well, so too, a room actually resonates in the same way that a string does. So, and it's based off in just the same way a string, if I have a longer string, it's going to resonate at a lower frequency. The same thing with a room. If I have a longer room, it's going to resonate at a lower frequency. And if I make the room smaller, it's going to resonate at a higher frequency. Just like if I put my finger on a fret of a guitar, it's going to reduce the string length, and therefore it's going to go resonate in a higher frequency. That's fine. Whatever. I don't know what's going on with my computer today, but we have this idea that basically we're trying to that these room modes resonate. The rooms resonate, and because they resonate, they ring, and when they ring, they hang on for a long time. So actually, this is a good example of it. This room is resonating right here at 70 hertz, and so even though the music blasts and it stops, the 70 hertz is going to continue on for a long time, and that's bad because it gives you an imperfect. And it also leads to it's ununiform, meaning if I were to take a lot of snapshots, acoustic snapshots around the room, this is going to change drastically. So in some parts of the room, this is going to be massively long. In other parts of the room, it's going to be in this case, it's huge. In other parts of the room, it's going to be a valley. So that's bad because what we want is we want diffuse because we want everybody in the room to have the same experience. So that it's not like hot spots of certain frequencies. So as I move around, we want that to be uniform all through the space. So the way you can do this is, the way I do it is basically I draw a piece of paper, I map out the standing waves of a room, and I go, okay, I know what the waves of a room are. And then I go out with a microphone and I measure it and I confirm it to see if my theoretical model, my math actually matches what happens in real life. And it actually does most of the time. It's pretty cool. It's pretty neat. But what's crazy to me is taking these sweeps. I guess I didn't clarify there. So basically, there's two ways we can measure a room. We can take peak noise and stop and measure the decay. The other one is we do what's the impulse one, which is what I'm talking about, where we do the sweep or a balloon. Both of those are impulses. A sweep goes whoop, and then what they do is they do some fancy math magic and squish everything to time 0, and that's how you get an impulse. And an impulse is all frequencies at the same time. The other one is to use like a balloon pop or a starter pistol or something that's a gigantic impulse of energy, and that just adds a ton of energy into the room. And you listen to everything that hangs on afterwards. So and the impulse method is by far the most common way of doing it, and the traditional way of doing it is with balloons, and the more normal way of doing it these days is doing sine sweeps. It's a little more uniform. You can do a lot more with the sine sweep. Your signal noise is a lot better. And that Room EQ Wizard software is great at doing it. It's super, super, super simple. So Noel said there in the comments, it's pretty interesting, said be sure to use red balloons. So there's this thing, like basically when you blow a balloon up and you pop it, what you want to have happen is you want the impulse to emanate as a sphere in all directions, which means you need to have it break at a certain like the way you can do a good balloon pop is when you pop it, you should have as many shards as possible. Like a balloon should break into many different points. That means that the energy exploded out in different directions. And red balloons happen to like they've done these studies, and like basically red balloons are known to be the best ones for doing this. Does it really make a difference? Probably not, but it's kind of been this thing that's propagated through the industry for a long time. Because the dye apparently is like in such a way that it makes the balloon pop in a certain way. So the physics of a balloon pop are pretty interesting though. I've sat in a couple talks on this stuff. It's pretty interesting. So, all right. So geometrical irregularities. So when you want to break up the room bones and disperse the energy around the room. So if we think about this, what we want to do is, so let's imagine this, what we're trying to accomplish here. So I've got this sound source. It could be a speaker, it could be a singer, it could be a violin, it could be anything in the room. But what we want to do is we want the energy to be diffuse around the room as much as possible. So knowing what we know about reflections. So when we think about a reflection hitting a concrete wall, the angle of incidence is going to equal the angle of reflection. Well, what we want to do is we want to actually break that energy up so that basically we want the energy to stay in the room, but we want to break it up so that it's not these specular reflections are just not these constant reflections. And the way we do that is by throwing geometrical irregularities, meaning we put stuff on the walls or in the room. Because if I put a hard surface, we know that it's going to bounce off that room. But if I make it into like a weird shape, it's going to hit that, and the energy is going to reflect off of all the different surfaces that it's hitting in different angles. So things like we mentioned, like bookshelves. So bookshelves are really good at this. Books themselves actually absorb a lot of sound, which is kind of bad if you're trying to keep the energy in the room. But because if you think about a bookshelf is going to have lots of different like depths with it. And so the sound energy, when it hits the room, it's going to reflect off the closer stuff sooner, and then the deeper stuff later, and it's going to break it up, or it's going to have different shaped surfaces there. So, but it could be any objects that have different facets, or faces, shapes, and depths and angles. So this is what you're looking for. But here's the interesting thing: must be at least 1/7 of the wavelength size before it starts being effective. So if I want to look at something like let's do some quick math here. If I want to break up, let's break up 2,000. Let's do 1,000 hertz. That's a good middle of the road one. What's the wavelength of 1,000 hertz? Help me out. So what I'm asking you to do here is V equals F times lambda. I don't have my iPad with me, so I can't switch over to that. So V equals F times lambda, right? So V equals F times lambda. So I always start with that one because you can always quickly algebraically do there. So I'm asking for the wavelength. So I solve for wavelength. So wavelength equals V over frequency. 344 divided by 1,000. So right there, I don't know if you can see that. So wavelength equals 344 over 1,000, which equals what? 0.344? 4 meters, which equals 34 centimeters. So 34 centimeters. So the wavelength of 1,000 hertz is 34 centimeters. Something like that. I don't know. We'll say 34 centimeters. But what we're saying here is that the objects must be 1/7 of the wavelength to start being effective. I don't know where that 1/7 comes from, but basically 1/7 of that. So if I do 34 divided by 7, I'm gonna do that as a calculator. I don't feel like. So if I do 34 divided by 7, so it needs to be about 5 centimeters. So that means the object needs to be on the order of around 5 centimeters on up a little bit to be effective to that. So let's do another one. So let's say so basically things that are small will affect small wavelengths, which are high frequencies. Things that are big will affect low frequencies, which are low frequencies, which are big wavelengths. So if I do something like let's look at 100 hertz. So 100 hertz. So where's my calculator? 100 hertz is going to be 344 divided by 100. 344 or 3 meters. So we could say 10 feet more or less. So what's 1/7 divided by 7 is 1/7 of that is going to be 0.49 meters. So that means if I want something to affect 100 hertz, it has to be at least yay big on up to affect 100 hertz. Because anything smaller than that, it's the diffuse, like the diffraction properties, it just wraps around it like it doesn't even exist. So you have to have big things to affect low frequencies and small things to affect high frequencies. So you have to use a combination of the two of them. So yeah, so it must be a seventh of wavelength to start being effective. And like we were talking about with this whole diffraction property, it's a gradient. It's not like, yes, it reflects off this thing and like if it's a small object in a large wavelength, it's not going to see it. And if it's a big object, massive object in a small wavelength, it's going to see it as a flat surface because the wavelength is so small. So again, you have to have this kind of combination of the two of those. So what about this? Absorbent patches. So spreading absorption patch materials work much better than grouped up. I don't know why this is in this chapter, but we're going to be talking a lot more about absorption coming up. So, but just as a general strategy, we'll just talk about this right now. So say you have a bunch of acoustic tiles, like the Oralex acoustic tiles. To make them much better, you should spread these around the room on a wall. You shouldn't bunch acoustic materials up on one spot. And this is tough because like when I deal with like acoustic projects, like say I'm working with a restaurant and a restaurant, so they come in, they're like, yeah, it's so loud in here. Is there a way you can remove it? Because in modern design aesthetic, we tend to like things to be hard surfaces. Like carpet went out the door in the like 80s, right? Like if you'll still go to some like steakhouses or some like 70s and 80s like restaurants that'll have carpet in there. But carpet in restaurants nowadays seems kind of strange because it just seems kind of gross. They've got food and stuff in there. But like I remember I was a busser. My first jobs as a busser, I worked in a restaurant that had carpet and I had to vacuum that carpet all the time. It was gross. I actually used one of those little sweeper things, but then at night I had to sweep it up. I had to vacuum it. But those restaurants, those older school restaurants, they're much quieter. And then these much more modern restaurants, when you have hardwood floors and concrete floors, and then hard surfaces and then hard ceilings, like that's the kind of the modern design aesthetic is to have a lot of hard surfaces. But then it's super reverberant. So the term is reverberant, but what people say is echoey. That's not the right word, but reverberant is the right word. But we know what they mean when we say echoey. That basically we're trying to they want to reduce that. So when I'm called in, they're like, hey, can you make this thing quieter? And I'm like, well, yeah, I can throw acoustic tiles all over the ceiling. And they're like, yeah, but that's not the aesthetics we're looking for. Can we just put all the tiles over there on that wall over there? You're like, nope, you got to spread them around for it to be effective. So, and this is something I go back and forth with designers quite a bit. Like, I'm like, so the challenge is to make acoustic materials that fit the space design ways. And for recording studios, that's not a problem. Like, we're used to seeing acoustic materials in there, but if you have like a clean gallery look, like gallery type spaces drive me nuts because they're so reverberant. But people want this, they want these really stark white big places, but like for living rooms, and then they have big glass walls, and they want it to be like this really like hard clean design, but it's so loud in there because it's so reverberant. They're like, can we cut that down? You're like, yeah, you gotta put space in there. Like, oh, I don't want to break the lines of the room. So that's kind of the design challenge with this stuff. So I kind of go at it with some designers sometimes about that stuff. Okay, so polycylindrical. Let's talk about our first strategy here. So if we want to break up the room, let's talk about polycylindrical diffusers. So last time we were talking about like convex, or was it last class? I don't know which class it was. We were talking about convex diffusion. So we know that when I have a convex diffusion, when the wave hits it, that it's going to break the wave up. It's going to spread it in different directions. So we can take a convex surface and make it out of hardboard or something similar, something that's kind of flexible, but hard but flexible. So a hardboard is like that, like stuff you can get at Home Depot, and then it's very effective. Remember reflection? So basically, they tends to diffuse high frequencies and absorb and radiate low frequencies. So dimensions aren't critical, but must be compared to wavelength. Shouldn't be range symmetrically. So here's an example of something. So this is like, must be some audiophile listening room. And what we can see here in this space, they've got these polycylindrical diffusers back here, and they're arranged in here. So if we imagine right here that if a sound wave is coming in and hitting this, it's going to break it up in the horizontal plane right there. So it's going to break this one up in the horizontal plane, and so it's going to do lower frequencies better because it's a larger one. These smaller ones are going to break up the higher frequencies better because they're the smaller ones. And because if I have a low frequency, a low frequency is going to have a long wavelength. It's not going to see this. It's going to see this. It's going to diffract around this thing and not even see it. It's too small to imagine it as being very effective because the wavelength is so large relative to this object right here. So but this is only going to work in the vertical direction, or sorry, horizontal direction. So what they've done here is they've mixed it up by sticking some in the vertical orientation, some in the horizontal orientation right there. And also by breaking up these different sizes. And then they threw some lights in there behind them to try to give them some aesthetic appeal to them. I'm not in love with the look of this thing, but I imagine that's pretty effective right there. So, another way we could do this is if we use like spheres, like hemispheres, right? So hemispheres would work, but hemispheres of different sizes I think would look really cool and give it this cool looking shape. But hemispheres are hard to make on your own unless you have like some sort of fabricator that you can do this. Because making hemisphere like this, I can just take a panel and I can bend it. I can go to Home Depot and buy a panel and just bend this thing, and I can just throw a frame behind this thing and it works really well. So these are very effective. We can also see that there's some other diffusers. So like if you look on the ceiling right here and right here, these are like the commercial ones right here. So what these are diffusers. So they've got these little ridges for the high frequencies, and they've got bigger ones for the low frequencies, and they've also got them in the vertical and the horizontal axis to try to break up the wave right there. So these are crazy. There it goes. I'll install it, but man, I don't know what's going on with this computer right now. Let's get back to this for now. But this room is like basically in this listening room, they've taken the angle that they want to have a fairly diffuse sound field. Okay. Sorry. I'm gonna let this thing. I'm gonna put this on my other screen. If I have time, I'll let it do its thing. All right, let's go back to allow. Okay, fine. So this is a pretty good example of this this, but like in this room right here, they're opting for fairly like reverberant room. So if this is a listening room, and I imagine this is so they've got some fancy ass speakers just right on off the page right here. Maybe it's a home theater, but what they're doing is they want the energy to fill the room, and we like this because we like the energy to immerse, like the sound energy to be around us. We don't want to feel like, well, for this person's perspective, we don't want them to sound like the speakers are right there in front of them. They want it to feel like they're in the space. So if they're listening to some classical music, it feels like they're in like a reverberant space and there's sound all around them. So you like to be like swimming in that sound field. So so here's another one. Like I just pulled off the thing. It's a kind of an interesting idea. It's kind of a fractal approach. So fractals are used a lot for this reason because it's a repeating pattern. So we see that in this case we have a large polycylindrical diffuser right there, and then we have smaller ones on the front right here. And this kind of goes against what they were saying is don't make these regular spaces because you create room modes. Aesthetically, it looks pretty nice, but you can create some weird constructive and destructive interference patterns off of this thing. But this is obviously a 3D model, but this is in a concrete room, and so if you want to break up their energy in the room, so if you don't want the flutter echo, like you don't want that flutter echo to happen. You want to break up the energy, but you want it to stay in the room. This might be a pretty good strategy right here. I think they look pretty cool aesthetically, so that's one strategy right there. But like they were saying, you shouldn't do this too symmetrically. You want to break those up. I like the idea of doing like the hemispheres and breaking those up. I think that'd be really cool looking. But yeah, like making hemispheres is pretty tricky business. So yeah, so those are basically, in a nutshell, diffusion. So again, I just want to make it very clear what we're trying to do here. So diffusion is where we want to keep the energy in the room, but break it up and spread it around evenly. So that's what diffusion is in a nutshell. Let's see if I got Room EQ. Okay, I got Room EQ Wizard working. Yeah, let's see if it works. I only have like 2 minutes. So, okay, cool. So I can't take a room cancel. I can't take a measurement right now because I don't have, well, I guess. Let me see if I could do this. I might be able to do this. Let's try this. I'll do this at 48K. Outpost left. Just so you can see what it looks like and kind of maybe even hear it. I'm gonna turn on my speakers. I'm using my headphones right now, but I'm gonna turn on my speakers so this works. See if this works. Default input is 1. Let's try it. So first thing I'm gonna do is I'm gonna do a sound level generator. Let's do this at pink noise. Okay. I might have to go to my system prefs. And then we got to get out of here. So, oops, not that security. Safety. Where is security privacy? Did I allow it? Yeah, okay. Let's try it again. Let's go -20. Let's do pink noise. Okay, so I'm just going to do this. It's so you can see what it looks like and hear it. Sounds like it. Continue anyway. Let's do minus. Let's go -16. Go. Whoops. I only did it to 200 hertz. All right, we got to get out of here. All right. I'll do more of this next time. Let's go to 20,000 hertz. You can see it. Cool. All right. So this is basically what we did here is we just did a room measurement. And so that's my frequency response right there. And I can look at my decay or my waterfall right here. Generate it. And bring this down. Whoops. I went way past it. Let's do 20K. And bring this up. So what we're looking for here is pretty smooth decay right there. And so this is like this, my room is super dead. So I don't have a lot of, and also this is looking at it backwards. My microphone is not facing the speaker, but this is essentially what we want to start looking at here. So we're going to spend a lot more time looking at Room EQ Wizard. I strongly recommend that you download this and start experimenting with it. But the biggest challenge I find that for people is that downloading or taking measurements is easy. Interpreting measurements is hard. And so that's going to be that's what we're going to be focusing on for a lot of the rest of the semester is understanding what these measurements mean and how to interpret them and then how to work to act on those. All right, my friends. We'll call it there. So sorry I went a little bit over today. So I'll get this thing posted and we're going to do comb filtering next class, which I think is really interesting. And then we'll dive into like midterm stuff for next week. All right, my friends, have a killer day. Thank you.